So let's go back to our thermal winds, because we can then move into the real world to see how the thermal winds temperature gradients are balanced in the real atmosphere, right? So we did thermal winds in pressure coordinates by starting with our density being a function of temperature, because we wanted to get rid of the barotropic or homogeneous fluid approximation. So we had written density as rho ref plus sigma, where sigma was the temperature dependent function. So dug dz, dvg dz in that case, where g or rho ref times d sigma dy or minus d sigma dx, depending on x or y directions. For compressible fluid, we want to go to the pressure coordinate, and we do it exactly the way we have done it all along, by going to our hydrostatic balance, which is a convenient vertical balance. So we flip it. Instead of writing dp dz equals minus rho g, we say dz dp equals minus 1 over g rho, where rho is rho ref plus sigma, right? So take our geostrophic equations in the pressure coordinate, which you had written before as minus g or f dz dy. Remember, dp dx dp dy can be converted to dz dx dz dy in the pressure coordinate. So let's take the p derivative of the x component of this equation, ug equals minus g or f dz dy. Why? For doing the vertical shear, so far we have been looking at dug dz, how winds change in the vertical, but in the pressure coordinate we have to see how winds change with pressure, right? So fairly simple. dug dp is minus g or f d squared z dp dy. Just took the equation, geostrophic equation, and we took the derivative with respect to p. We can rewrite it as minus g or f d dy of dz dp, where dz dp from our hydrostatic balance is 1 over g rho. So g cancels out, and you have 1 over f. So this has minus g rho, right? So minus minus cancel. You have 1 over f d dy of 1 over rho, but now we are in the pressure coordinate. So constant p refers to the pressure coordinate. What do we need? Obviously, back to our ideal gas law, we need 1 over rho. So 1 over rho is RT over P, right? So if we write things in terms of T and P, we can get rid of density, which is always our goal. So d dy of 1 over rho in that case becomes R over P dt dy. I'm not going to go through this step, but you can easily do that, right? So this is again in the pressure coordinate. So now we have reduced the vertical shear of the geostrophic winds to meridional gradient of temperature. Why? Obviously we are heading towards thermal winds. So dug dp and dvg dp are then r or fp dt dy p for the x direction, and minus dt dxp for the y direction in the pressure coordinate. So that looks kind of parallel to our geostrophic balance. Instead of geostrophic winds, we are writing geostrophic shear. We did this before as well. So what does it say? Height contours on pressure surfaces. Remember, pressure surfaces are not parallel to z. They are up and down, like the geopotential height that went from 5.8 kilometers to about 4.9 kilometers at the poles. So you can draw constant height contours on those pressure surfaces, which is what a geopotential height is essentially. So height contours on pressure surfaces are streamlines of geostrophic flow. We had even defined the stream function, and we had done the derivatives. Okay, what we are doing is now putting in a parallel. Temperature contours on pressure surfaces are streamlines of the thermal wind shear. Do you understand the difference? Geostrophic flow appears as contours of height surfaces on height contours on pressure surfaces, whereas geostrophic shear or thermal wind shear appears as streamlines of temperature or contours of temperature on pressure surfaces. So we can look at this and we can avoid density, obviously. So here is our wind shear, and we want to relate it to the temperature gradient in the pressure coordinate, right? That's what we will do in the next podcast. Okay, thermal wind is basically shear of the geostrophic winds, right? We had done it before as vertical shear, but for the atmosphere it's always convenient to go back to the pressure coordinate and do it as shear in the pressure coordinate. Why do we want to do it? Because that'll allow us to interpret these meridional structures of winds in terms of thermal wind balance, which is basically a combination of geostrophic winds, hydrostatic balance, and meridional gradients of temperature or density.